Hello everyone, this is Vishal Sarin. I'm CEO founder of Sagence AI, and my talk today is about chiplets and how they are necessary for viable scaling of inference from edge applications all the way to data center applications. I will really focus a little bit about how we use chiplets, and we are an analog and memory compute technology that finds it extremely useful to leverage what chiplets bring to boot to get extremely low power, extreme low cost, and high performance, an absolute requirement for the industry as we get into mass adoption for inference use cases. A little bit about our core technology as I explain how technologies can be integrated with digital compute to enable the best power performance required for scaling. GPUs, essentially, if you look at them, they are very power hungry, and most of the power comes from essentially two elements. One is MAC compute, which is multiplication accumulation compute units, and the second element of that is memory access. Both of them are very substantial in terms of the power consumption in GPU compute and the memory ecosystem around it. What we've developed as an example is a core technology that lends us to up to 100x improvement in power performance. But the way we do that is that we leverage non-volatile memory cells and we integrate both compute and storage into single transistors. So at the first step, the first advantage is that we are integrating compute and memory, eliminating all the bottlenecks of data movement between compute and memory and power consumption between compute and memory. Secondly, we use multi-level technology. This gives us a 24x advantage in terms of storage density because we use one transistor, whereas you need to use 24 plus transistors to save the same amount of data. Thirdly, we use the same transistor to do our MAC computations, normally done in over 500 transistor implementations in digital processors. So these are very substantial benefits that our technology brings to boot. However, it's a technology that requires embedded non-volatile memory. You can look at it similarly when you're looking at optical technologies or other embedded memory technologies that you might want to use to get very high efficiency in terms of AI compute, specifically in this case related to inference. If we look at really any kind of neural network graph, most of the compute in any neural network graph comes from matrix multiplications. That is approximately more than 95% of your compute, give and take, comes from vector matrix multiplications. What we are doing here is we are taking all of that compute and we want to move it to our analog in-memory compute, which is multi-level, deep subthreshold compute with integrated memory and storage into the same transistors. That gives us a huge advantage. But while we do that, we also want the flexibility to be able to operate many different types of neural networks. So if you look at the graph of what a neural network looks like, whereas we move the vector matrix computations into analog compute, we like to retain the rest of the computations in digital, where you get the maximum flexibility from compute. By breaking it up, what does it give us? What it gives us is on the analog side, we can do computations in 2 femtojoules per MAC operation. That is substantially low energy computations for fundamental MAC operations. We have zero power consumption for data movement for our models, from parameters to whatever is the compute element, since we integrate memory and compute. And we have very low intermediate storage power consumption as well. So this allows us, if you think about it, what chiplets allow us to do is separate out the analog process from the digital process, because on the digital process side, We want to use low power SRAMs that are best done on digital processes for 7 nanometer, 5 nanometer, 3 nanometer nodes. We want to implement our digital compute for pre and post processing using on SIMDs, and we want to use digital processes for low power, high speed I/O, input output, for our chips. So we are leveraging chiplets by separating out the analog compute and the digital compute in what provides us with the most optimum power consumption and cost benefits for getting overall best power performance. If we go forward and look at this in terms of how industry can leverage this, very much like how we are doing it, industry can look at what kind of computation you like to do, where you move, for instance, E-flash or resistive RAMs, gallium arsenide computations on optical side into nodes that are most efficient for in terms of both power, performance, and cost for those kind of computations. While you keep the digital computations on what is most flexible and most optimized for digital compute, such as 575 3 nanometer nodes for digital processes. Also, chiplets allow you to then keep your memory in processes that are most efficient for memory. For instance, digital, you can have DRAMs or SRAMs where the process is most optimized for storage for the kind of memory that you want to use, including NAND flash as such, right? So what chiplets are allowing you to do is use a heterogeneous mix of process nodes to get most efficient performance at the lowest power and the lowest cost, because you're optimizing your process nodes for the kind of workloads that are required to be performed for those particular process nodes. As you do this, as you break it down into chiplets, your die sizes typically get reduced. Instead of having a large SoC with everything integrated into it, the die sizes get reduced. This allows you to improve yield. Smaller the die size, higher is the yield. And so it really helps you to optimize across different types of workloads in terms of how much memory you need, how much digital compute you need, how much analog compute you need, and also in terms of improving yield and reducing cost for compute, which is very critically needed by the industry for economic viability of large deployments for AI. With that, I would like to talk a little bit about scalability, because chiplets really allow us to scale for very many different use cases. As an example, for us, we use for factory cobot kind of applications, we use 3D integration. We put a couple of our chips, analog and memory compute chips, with a base digital chip, and it's typically two AIMC chips with a base chip. And that serves very well for those kind of applications, depending on the model sizes that and the throughputs that we are trying to look at. If you look at humanoid robots, there again, we are using 4+ AIMC chips with a base chip. Again, allows us to scale across different types of model kinds and model types, and also allows us to, we don't have to limit ourselves, by the way, to just one 3D chip. We using interposers and integrating both 3D and 2.5D integration, we can use one or many of these chiplets on an interposer as well. And then as we go to data center grade applications, we use 8+ AIMC chips on the same package. So this is an example of how the industry can use different configurations of heterogeneous mix of process nodes to scale for many different types of end use cases and applications. By using both 3D packaging as well as 2.5D chiplets on a 2.5 on a interposer integrated. This is where the industry needs to go when we want to scale forward. With that, I'd just give you an example of what it can achieve when you optimize your workloads like that. For us, if we compare ourselves, for instance, with the latest, greatest, the latest cutting-edge GPU in the industry today, we can increase the performance for inference by more than an order of a magnitude. To top it off, normalized for performance, we can get the same performance at 9 times lower power consumption. And on this one, we are looking at Llama 70 billion model as a metric, as a model for comparison. We can also, at the same time, reduce the cost of compute. Like I said, most of our compute is going into, for instance, a 40 nanometer node. And this is, by the way, true for whether people are using resistive RAMs or using other kinds of technologies. Once they optimize the cost of the compute with the kind of technology they are using, they can substantially reduce the cost overall of the system performance. So in our case, since we're using 40 nanometer for more 95% of our compute, our cost of compute goes down substantially, so that the overall system performance or overall system cost for normalized performance is 5x lower for us. And of course, the same goes with the amount of rack space we can save when we can get an order of magnitude higher performance. That means for the same performance, we can get an order of magnitude lower in terms of rack space for data centers and such. This is the kind of advantages you can get if you have a core fundamental technology and you leverage chiplets, both 3D and 2.5D technologies, to come up with overall best-in-class system performance for inference workloads. Talking a little bit about where we want to go from where we are today. We do see a need for a larger interpose areas. This is because we can then conglomerate a larger number of chiplets on the interposer to provide for better, higher performance and lower power consumption, as normalized for performance, of course. This, going forward, we're talking about just a couple of years ahead of where we are seeing now. We can see that we can get a boost of about 50% in terms of throughput by increasing the size of the interposers available over the next 2 to 3 years. Another area that we think we can improve is in terms of 3D stacking. We want to be able to stack more and more chips for better 3D integration, as well as the size of each chip. This comes from the fact that depending on what the compute requirement for the base chip is, depending on what the requirement is in terms of in-memory compute, how much memory you need for larger and larger models, there is a need for increasing the die size on the stack. Certainly, we improve yield when we go smaller die sizes, but there's an optimum there, and we'd like to see that increase, and that actually can double the capacity for us going forward. We're talking to folks to be able to do that. A big aspect of chiplet technology is when we are integrating, making compute denser using interposers and 3D stacking. It also becomes important to try and manage heat generated in the packages and in the interposer. And we find that we can, certain technologies such as microfluidic cooling and also some architectural innovations which are AI-driven power allocation and so forth, can further reduce power consumption by about 25% or so. A third aspect of what we see the industry needs is higher density through silicon vias, higher density through silicon vias and interconnect on the 2.5D, on the interposers. So both on the 3D side and the 2.5D side, we would like to see higher density interconnect, and that we think over the next few years will enable us to get to almost a 40% higher bandwidth for data movement. All of these combined advantages play out for us as we look at various aspects of chiplet technologies, both 3D and 2.5D, as the industry scales into chiplets for better power performance, better cost performance, and and other elements which I will talk a little bit later in terms of how chiplets can help us in a very substantial way. So I already talked about heterogeneous integration. I talked a little bit about yield improvement and cost efficiencies coming out of that. How you can really bifurcate different kinds of compute to optimize on different processes for overall higher throughput and performance. But chiplets provide for a lot of other advantages as well. One is thermal management. It's very hard to manage a lot of heat on very large SoCs and GPUs. So as you break them out up into smaller chiplets, heat can be better managed. That's one aspect of it. Second is the modularity of scalability. For instance, you can have now solutions where you can have different configurations of compute with memory. You can choose how much memory and how much compute you need at a system level by using chiplet technologies. Better interconnect bandwidths are enabled by when we use interposers and also through TSVs. This is again talking about both 2.5D and 3D integration with chiplets. And this is absolutely needed as data movement requires are constantly increasing in the industry. And then there are other aspects that the technology lends itself to in terms of advantages. One of which is, it supports incremental upgrades. Now, what I mean by that is, let's say you have really split up your, your solution into a 40 nanometer process node or a 28 nanometer process node, and another which is analog centric as it is in our case, but it could be resistograms or optical, what have you. And if you are upgrading that particular design or making edits to that particular design, you don't have to run a new piece of silicon on a 3 nanometer node, which is extremely costly. You could run it on a 40 nanometer node to fix that problem, which is 1/20th the mass cost of what a 3 nanometer node might be. So again, there are a lot of advantages there. There are advantages in enhanced testing and binning areas, because you can have now analog processes, for instance, and designs require tighter calibration and different kind of binning than do digital, and now you can separate out and optimize those separately in terms of your test platforms. And last but not least is a design reuse. You might want to spin a new chip, but what you need to change is possibly your digital implementations or architecture without making any changes to your analog compute nodes, as an example, or your optical compute nodes, as an example. All of these come about from the heterogeneity of chiplets that chiplets provide in terms of smaller chips, different kinds of processes optimized for different kind of end use cases, different kinds of embedded technologies, and so on and so forth. So I will conclude by saying that chiplets are the way forward for the industry to enable scalable and high performance inference workloads, which allow us to be very modular in a manner of speaking, to build, to address use cases from edge use cases all the way to large language models in the data center, and do that in a very cost efficient and a very power efficient manner. Thank you.